Look at the start of a relay race. The athletes aren't lined up in a straight row. Instead, runners in the outer lanes are pushed significantly forward, starting meters ahead of the inside track. This stagger is a matter of fairness. Because the outer lanes form wider curves, those athletes have a longer path to travel. Without this head start, a runner in the 8th lane would actually run much further than a runner in the 1st. Measuring the distance around straight-edged shapes is predictable. For a square, you just total the 4 sides. For a rectangle, you double the length and the width. But racetracks aren't built on right angles. To calculate exactly how much of a head start is needed, we have to move from straight-line math to the boundary of a circle, the circumference. Every circle has 2 primary measurements. The outer border is the circumference, and the straight line through the center is the diameter. Divide the circumference by the diameter, and the result is always the same. Whether a coin or a stadium, this ratio never changes. This discovery provided a reliable bridge between straight-line geometry and the curves of the natural world. It meant that for the first time, any circular boundary could be calculated with the same precision as a flat wall. Mathematicians call this constant ratio pi. Ancient civilizations spent nearly 4,000 years chasing its exact numerical value through geometry and observation. They realized pi is an irrational number. Its digits go on forever without a repeating pattern. This is why we use approximations like 22/7 or 3.14 for most of our daily engineering. By rearranging the original ratio, we get the definitive tool for measurement. Since c divided by d is pi, the circumference is pi times the diameter, or as we usually write it, 2 pi r. This formula allows us to quantify the total length of any circular boundary using only its radius. We can apply this logic to pieces of a circle too. A semicircle is simply half of that formula, or pi times the radius. But what about a specific smaller curve? A full circle is always 360 degrees. To find the length of any specific arc, you take the full circumference, 2 pi r, and multiply it by the fraction of the circle that the arc covers. This is how we solve the racetrack problem. On the straight stretches, every runner covers the exact same distance. The only difference in their journey happens at the 2 curved ends. Because lane 2 has a larger radius than lane 1, its curve is longer. By calculating the circumference for each specific lane, we find the exact distance needed for the stagger. Using the arc length formula is how track organizers ensure that when the starting gun fires, every athlete is running exactly 400 meters to the finish. We've measured the line, but we can also measure the space inside it, the area. Archimedes used a brilliant visual method to prove the area formula. He visualized the circle as a collection of thin layers and unrolled them into the shape of a right-angled triangle. The height of this triangle is the circle's radius. Its base is the unrolled circumference, 2 pi r. Following the area of a triangle, 1/2 base times height, we multiply 1/2 by 2 pi r by r. The 2's cancel, leaving us with the familiar pi r squared. It's an elegant symmetry. The space inside a circle is determined entirely by the constant relationship between its radius and its perimeter. Here is your summary for circle geometry. These 3 formulas are the essential tools for calculating circumference, arc length, and area. With these, you can accurately measure and construct any part of the curved world around you.